topic for the day will be conditional probability. Usually I like to introduce the concept first and then try to explain what it is and then name it. So here we'll name it because the things here, if you can see, this is there are two words, conditional and probability. Probability, more or less we have seen what it means, and then we'll see what is conditioning part, what is this condition about. The first thing you should know is, I told you one thing. I told you that everybody has a belief about the world that he's around or he or she is around. So, and you also assume that if you are a quite normal human being, you will assume that we don't know everything, okay, and we have uncertainties. So we have a belief, and we also know that it's incomplete word knowledge, and we have a belief based on whatever incomplete information we have. So the more we get to know about the world, we try to update our belief, okay. The statement that I made is, with new evidence you should not change your belief, you should update your belief. So with new evidence you should update your belief. So this is a general notion. So people, whenever they know something about anything, and after they find some new evidence, they update their belief. Okay, so that's the one thing, that belief is called as prior. So we have a prior knowledge. We know prior about something, and after getting the evidence, you update the belief. Now the question is how to update the belief. Okay, this how part. How to update the belief. This is what will deal in conditional probability. Basically, conditional probability use a framework of updating the belief. In general, probability is a framework of dealing with uncertainties. You have uncertainty in something, you model it by using a probability. But now if you have some belief, by belief I mean you have some world knowledge about something. Even in the previous session we introduced that some things cannot be simulated. Okay, let's suppose if I say, what's the probability of Trump becoming a president? So you can't simulate it continuously. If you have to do it, you have to have prior belief, and based on that, once you get evidence, you will update the belief. And sometimes probability is called the measure of belief. You measure the belief, and that's called prior. So now I said, with the new evidence you should update your belief. Now how to update the belief? Now this conditional probability will help you us in that, how to update your belief. Okay. So what is this condition? I'll take a simple example. It's very it's conceptually very simple, but its implications are so deep. Okay, and implications sometimes seem so counterintuitive, and brain is not ready to accept these claims whatever conditional probability makes. Okay, so let's take a simple example which we discussed briefly in previous session. Let me again go through the example. So let's suppose you have two die. You have two dice. This is one dice and this is another one. It's numbered. It's faced a number from 1 to 6. So and you roll these two dice. You roll first die and you roll second die. So now you know all the possible outcomes. You know that. So all the possible outcomes, if it is a six-sided die, six-sided dice. So what we have is possible outcomes. So I can write the experiment like this. So I can write it D1, D2. So this is the number on the first roll and number on the second roll, or number on the first die or number on the second die. So you know the outcomes possible are the total number of outcomes, that is sample space. I'll write S. S will be 1, 1, 2, 2, and so on till 1, 2 till 1, 6, 2, 1, and so on till 2, 6 till 6, 6, something like this. There are 36 possibilities. 36 possible outcomes are there, and now it makes sense to assume here that each of this outcome is equally likely if the die is fair. So you can say that each of this outcome is equally likely and the probability is 1 by 6. Now if a question is asked, let's suppose a question is asked that what is the probability that sum of top faces is 7. So when we roll this die, I'm just saying it in the words and then you can write it formally. So probability that if you roll these two dice and then you sum up the top face number, the number can be 1, 2, number can be 5, 6, and sum of the top faces is 7. Okay, then what you will do is you will say, okay, now we had all these possibilities. So what are the possibilities? The number will be 7. It will be 1, 6. If the first die roll was 1, second die roll was 6, and accordingly we will have 2, 5. Then we will have 3, 4, 4, 3, 5, 2, and 6, 1. So these are the possibilities: 1, 2, 3, 4, 5, and 6. So these are possible. I said there are different ways to look at it. So we can see probability as area also. So we can think it like this. So if there are two dice, so this is 1, 2, 3, 4, 5, and 6. This is die 1. 1, 2, 3, 4, 5 and 6. This is die 2. So we have these dice. Now, so here this is represents 1, 1. This represents 1, 2 and so on. It is pretty easy to see it. And then I also said that you can represent it sequentially. So sequentially, how you can represent it? You can say 1, 2, 3, 4, 5 and 6. Okay, then for here this 1, 2, 3, 4, 5 and 6, something like this. Okay, this becomes a lot of clutter over here. It's better to represent it like this. Okay, so now the question is, this is our whole sample space. This is our whole sample space. If you see this, if I ask you the question, okay, sum of the top face is 7. So why is the sum of top face 7? So you can see that 1, 6, that is this. Okay, then 2, 5, that is this. Even you can see this whole diagonal. This whole diagonal, this is sum is equal to 7. The whole diagonal is this. So now you know that all of these have possibilities 1 by 6. So the probability of this, whatever we'll call it event A. Event A basically means the sum of sum is 6. Then, or we can say die 1 plus die 2 is 7, not 6. Die 1 and die 2 is equal to 7. So the probability of this is equal. This is 1, 2, 3, 4, 5 and 6. This is 6 divided by 36. Because each has 1 by 6 probability, and we assume that all of them are equally likely. So 1 by 36, this is 1 by 6. Okay, so this is the probability. Oops. This is the probability, and 1 by 36 is the probability of this is 1 by 36, not 1 by 6, 1 by 36. 1 by 36 is the probability of one outcome. So 1 by 6 is the probability that two dice will have the face up and the sum will be 7. Now you can see there are two things happening. There are two events happening. D1, what is on the dice 1, and D2, what's on the dice 2. Now what if I say that D1 is equal to something like this? I said I've observed that once I roll the die, the first die came out to be 2. Okay, then what should be on D2? Okay, I can what's the probability that now the sum will be 7 given that dice 1 is equal to 2. Okay, I'm writing this, I'm not writing it here, I'm saying it verbally. So what's the probability that the sum of faces is 7 on die 1 and die 2 given that die 1 is equal to 2? So what's the probability of this? Now you saw that we have condition on something here. This is conditioning. So we had two events now. The first event was rolling over first die. The second event was rolling over second die. And once I said that one event happened, I gave you additional information about something. I said this event happened. And now initially you might have some belief. Initially the belief was, let's say initial belief was this. This was our initial prior belief. The probability that both of these will sum up to 7 is 1 by 6. Now what I'm saying you, I'm telling you that this D1 is equal to 1 die occurred to be 2. Okay, the first roll was 2. What is the probability that some of the faces will be 7 now? Now you'll have to somehow update your belief. You'll have to update the belief because you got an evidence. The prior was 1 by 6. You have the knowledge 1 by 6. You said that, okay, even if I don't know anything, I have a prior belief because I assumed that all these outcomes are equally likely. So each outcome has 1 by 36 probability. So now I have 6 such outcomes which are favorable to me. So I'll say that I have the probability of 1 by 6. Now you got on the first roll, you got D1 is equal to, you got some event happened and you got some additional evidence. Now based on that evidence you have to update your belief. So that is where we'll use conditional probability. So probability sum of the face is 7 given something. So initially you were not given anything, you had a prior, you had some belief. Now you are given something. So based on this you have to update your belief. Let's see how to update the belief in this scenario. So D1 is equal to, now you see that D1 is equal to, so D1 is equal to, so this is my dice 1, let's suppose, and this is my dice 2. This is my dice 2 and this is my dice 1. Now I know that on on D1 2 happened. So on D1 this 2 happened. So this happened. So it leaves with me this only. Okay, it leaves me with 2, 5. This one. Okay, so if that thing happened now, I'll have to reassign the probabilities. I'll have to reassign the probability. If initially something was happening, now I'll have to reassign the probability. Let's make a Venn diagram to explain it. So this is something like this. So if you had a sample space like this, let's suppose you had an event like this, one event was like this, and you had end the event like this, something like this. It's considered like something like this. There's an intersection part as well, something of this sort. So this part is the intersection part. Okay, so let's say we'll assume this is part 1, part 2, and part 3. So we'll assign them some probabilities. Let's say this is 1 by 6. Call this intersection part 2 by 6. Let's suppose 1 by 6. This is 2 by 6. So now this thing should be given 3 by 6. Okay, to make it 1, because you know the probability should be equal to 1. So by following all the action of the probability, I said, now you can see this is event A. Let's suppose this is event B. The event A was there, event B was there, as we had dice roll 1, dice roll 2nd. Basically, I'm trying to come up with the formula, come up with how can I update the belief. I'm trying to do that. So this is my probability 1, probability of A. This is my probability of B. This is my probability of A intersection of B. Something like this. This is only A. This is A intersection B, and this is probability of B. Now I have 3 disjoint events over here, 3 disjoint things. Now let's suppose if somebody told me that this B happened. Okay, this thing happened already. Now this thing happened. If this thing happened, okay, initially I had probability of A, probability of B, something like this. So now if somebody told me what is probability of A given that B happened, initially I might have some belief. I had some belief probability of this is this, probability of this is this, something like this sort. Now I am being said that probability A given B happened now. So this over here, if you see this event over here happened now. Okay, this B event. Now I know that B event, if you see, there are 2 things in that. B had this 2 by 6 and 3 by 6, 2 by 6 and 3 by 6. So I have to compute probability of A given B. So what is A in there? So A is this part. Actually A was this whole thing was A. This whole thing was A. But now the A part left is this much. The A part left is only this much. So we have to compute the probability of this yellow portion given that B happened, because we assumed that initially our whole world was this sample space. The sample space was our whole world. But somebody gave us additional information that B happened. So now we will restrict our thing that now we know that this thing happened. The area of interest to us is now this much. Okay, initially it had the probability 2 by 6. The area of interest that was to us actually was whole this much, but somebody told us that B happened. We have to update our belief. So initially this was 2 by 6, and the part was 3 by 6. Now you can see that if this event happened, we have to somehow reshuffle the probability. We have to somehow tell, okay, this 2 by 6 plus 3 by 6 does not add to 1. Okay, if we have 2 by 6 plus 3 by 6, so it is 5 by 6. It is not 1. Okay, so we have to somehow normalize it. Okay, so how can we normalize it? So you can see that this is 2 by 6, this is 3 by 6. Then the ratio of 2 is to 3. Okay, so if these are 2 parts, this is 3 parts. So we have to normalize it in the same way. So we have this 2 by 3 and 2 by 6. We have 2 by 6 and 3 by 6. If we have to shuffle the probabilities, then we'll have to reassign the probabilities. We'll have to update the belief. So how can I update the belief? So I'll have to assign these, because I know for sure this thing is not happening. So I'll give it 0. But for these things, one is this yellow portion and one is this purple portion. I have to reassign the probabilities. Now I have to normalize them. So how can I normalize? So I have to do it in such a way so that I'll maintain this ratio of 2:3. I'll maintain this ratio. So what can I do is I'll have to divide in such a way so that I'll maintain this ratio. Okay, that is why this I have to basically normalize. And normalization should add up to 1, and once it adds up to 1, and it should be in the ratio of 2:3. I have 2 things to do. One thing is proportion should be equal. Proportion should be equal, and I have to normalize it. Once you make the proportion equal, proportion by equal, I mean equal as it was. Proportion not equal. Proportion should be as previous. So whatever it was previously, that should be the case, and then you should normalize it. Now by normalization, I mean the sum should be equal to 1. This is my goal. Okay, so what is the probability of A given this B? So I told you 2 things. Now B happened, somebody told me that there is no chance that this event is going to happen. Now I'll have to maintain the proportion, and then I'll have to normalize it. So the first thing is we somehow concentrated on this part. We concentrated on this part. This is my probability. So this is the probability that I am worried about, this yellowish part. But this is my whole B. Okay, so what I can do is I'll say that probability of A given B, I can write it whatever is the favorable part, my intersection part. Okay, this is probability of A intersection B. Okay, so this is my proportion part. I'll have to maintain the proportions in that. Okay, this is basically this part. I'll have to compute the probability of this, but I'll compute the probability. I had to normalize it also. Okay, so how can I normalize? I'll divide it by the probability of B. That's how it will normalize. Okay, so here initially if it was 2 by 6 comma 3 by 6, so I was interested in this case, 2 by 6 case. I had to normalize it also. Okay, I have to assign probability to this part, let's suppose to this part, but here the interesting part to us was this yellowish part. So once I'm assigning to this, so this basically is the probability whatever earlier probability it had. The earlier probability was 2 by 6. Now in order to maintain the ratio, so I am normalizing it. I am dividing it by the whole probability of B. Okay, whole probability of this B. So this B in total, basically what we are doing is, this is 2 by 6 and 3 by 6, and this is divided by B is basically add both of these, add this 2 by 6 plus 3 by 6, divided by same thing 2 by 6 plus 3 by 6, because this was the total probability of B. Okay, so if you see this 2 by 6, and now you will come to know this is 2 by 6 divided by 5 by 6, this is 2 over 5. Okay, this over here if you see, this is 3 by 6 and 5 by 6, this is 3 over 5. Now this portion if you see, this purple portion is 3 by 5 and this portion is 2 by 5. Now you again saw the proportions were maintained and I normalized it. Now if you see this, if you see 2 by 5 plus 3 by 5, so this is equal to 1. Okay, give me a second, I'll answer your question. So now what I said is, if I say a probability of A given B, so I assumed here B happened, the event B somehow happened. So I said, okay, if this thing happened, if I want to know the probability of A now, because I know B happened, so I'll be only worried about what is the intersection part, because I am sure whatever is not in the B did not happen. So remove that part. Only I am concerned about this part. So this was good enough. So I would have said, okay, probability is this much. But you know that I have to also follow the actions of probability. I have to normalize it. So how I can normalize it? Divided by probability of B. Question, yes. So initially I had the sample space. I said I have two events, event A and event B. So I assigned some probability to only A, only B and intersection of this. So I said 1 by 6. So this over here I said 2 by 6 and this over here is 3 by 6. I said now I have these events and I have three disjoint sets of these. Now if somebody told me, initially I had a belief about probability of A. So probability of A was 1 by 6 plus 2 by 6. So probability only A. Basically the probability of A I had was 1 by 6 plus 2 by 6. This was my earlier probability, that is 3 by 6, that is 1 by 2. This was the earlier probability I had about this setting. Now somebody told me, you know what, B happened. Now if B happened, so that means this portion happened, this portion happened. I have to remove all the things that are outside this B because I got an additional information that B has happened. So now if somebody told me what is the probability of A given B, so that means I am interested in this yellow portion. The yellow portion that you see over here, I am interested in this yellow portion, the one I am making red now. So this portion I am interested in. So I said that this should be equal to probability A intersection B. Whatever the probability was, I'll take that, this probability basically. But now I have to normalize it. If you see, there are two portions to this. This is the first portion, okay, and this is the second portion. I have this red portion, the only red, this one, and I have this yellow portion now to this B. So I am saying earlier they were in the ratio of, they were like this, they were 2 by 6 and 3 by 6. So this is my probability of whole B, probability of whole B happening. So now I have to equate this equal to 1. I am saying this 2 by 6 plus 3 this basically 5 by 6. This 5 by 6 is the probability of B initially. But what I have to make it equal to 1. So for this now, this is my 100% because this happened now. So I am saying now probability of A given B is the intersection part because I am left with only this part. I am only left with intersection part over here because all of the other things were removed because somebody gave me a new evidence that B happened. So if B happened, so that means probability of A intersection B, whatever is the intersection, okay, divided by the probability of B. So this is because I want to normalize it. That's what I said. If somebody tells me what is the probability of A, let's suppose given B, I could have written it like this also, probability of B intersection A. But you know that both of these things are equal, and probability of B. This is for the normalization. So this is normalization. Yes, questions. Go ahead. So now we came with the definition that probability of A given B is equal to probability of A intersection B divided by probability of B. Okay, this is the normalizing constant, and we saw that B happened, so we'll only be concerned about the cases of A that are in B, and P of B should be greater than 0. So this should not be equal to 0. Okay, this should be somewhat number greater than 0. P of B should be greater than 0. Okay, otherwise this will go into a different case. This will be mathematically incoherent. So this is the definition of independence. Okay, pretty easy. The first intuition I directly gave you, I told you that you have to use this. You directly can think of a world. Initially we had a world like this in which we had some objects. We had, let's suppose, 1 2 3 4 5 6 7 8 9 10 11 12, some 12 objects were there. Okay, so now if somebody told me that this was the initial event was something of this sort, okay, then some event was something of this sort, okay, something of this, and somebody told me that this yellow event happened, initially I was giving these as all equal probabilities. Now once somebody told me that let's call this as A and this as B, okay, let's call this as, let's say, A, this as B. Somebody told me probability, what is the probability of A given that B happened? Initially this was the world that you have, so you had all these points. Now what I am saying is, once this B happened, that means you restrict yourself to this yellow region. So in that you will be worried about this intersection part only, you will be worried about these intersection parts only. So you will say, so I am concerned about only this intersection part, but to normalize I'll have to divide it by the whole probability of B. Okay, now you can see this statement is quite easy. If you see this statement, this definition of conditional, not independent, sorry, not definition of conditional probability, this is conditional probability, and the independence is a topic that is coming. This is the definition of conditional probability. You can see that this definition looks quite easy, but if you see its implications, I told you implications are quite deep and profound. Okay, that we'll see by doing some examples. Okay, let's take the first example. You have to compute it and keep your sort of brains open so that you reason and then you come with the answer. So I'll ask you two questions. They'll be pretty much similar, but based on the probability, based on this conditional probability. Okay, let's take this question first. Let's say you have a four-sided die. You have a four-sided die of some of this sort. So I'm making a diagram of this thing. You have four-sided die, 1 2 3 4, 1 2 3 4, and it has only four-sided. Let's put a tetrahedral die, and this die, each side has the probability. That's 1 by 4. 1 by 4 is the probability on one die. So let's say you have two dice of this sort, and you are rolling them. Okay, you are rolling them, and then you are seeing numbers on them. Okay, so let's suppose if I tell you this. So if in a die roll you have these two rolls, X is the first roll, and Y is the second roll. Okay, the possible outcomes you can see is like this. So let's suppose an event. I'll define an event. Event is minimum of X comma Y is equal to. Okay, this is the event I have. The event is minimum of X comma Y is equal to. This is the event. So if I show you this minimum of X, Y, and 2. So all the things, if I have, let's suppose, something of this 3 comma 2. So if you see from both these die rolls, the minimum is 2. So this event will be taken into consideration. Okay, so the possible outcomes for this, let's suppose this is our event. So we have, this is our event. This is our event. Call this event B. So we have two dice, tetrahedral dice, and X is the first die, and Y is the second die, basically first roll or second roll. And then I am saying you this is the event, call this event B, and let's have an event M. So we have event B is this, event M, let's call it max of X comma Y. Okay, max of X comma Y is the event B. So what is the probability that max is equal, M is equal to 1 given B, and what is the probability of max is equal to given B? Okay, the question is this. How many of you understood the question? I made quite haphazard though. So the question is like this. In the question we have two dice, two tetrahedral dice. They have four sides. That's 1, 2, 3, and 4. And each of the side is equally likely. So when you roll these dice, so there is a chance number 1 will appear with probability 1 by 4, and all numbers accordingly. So you have these two dice. Okay. Now I am defining an event. The first event is, let's call this event B. Okay. This event B is defined like this: minimum of X and Y. So X is the first roll, the number on the first roll. Y is the number on the second roll. So minimum of X comma Y is equal to 2 is an event B. So I said I took an example like this: 3 comma 2. So if you see minimum in these two is 2, so this will come under this event. If I say 5 comma 2, so this also will come under this event, because the event is defined in this way: minimum of X comma Y. X is first roll and Y is second roll. Then the second event, second event is m, a max of x comma y is defined as m. I am saying what is the probability that maximum is 1 given that b happened? What is the probability that maximum is 2 given b happened? Can you compute the probability of both of these things? The question was like this. So if you had these dice now, the first thing is we'll see this is the event. So this is the event b, minimum x comma y is equal to 2. So all these events where the minimum is 1 comma 2, we will somehow see them as an area. So this is 2, and now this, let's suppose this is 1 comma 2. So here 2 is so here 2 is max. So we have to find min. So this 2 comma 2 is minimum, 2 comma 3, okay, 2 comma 4, and then this side also 2 comma 3, 2 comma 4. So this is event b, this is our event b. So if what I told you is that each of this is equally 1 by 4. That means now we have how many of these circles? So we have 16 of such. So each of this has 1 by 16 probability. If you see it in numbers, so each of these cells has 1 by 16 probability because they're all equally likely. Okay, so this is our event b. Okay, this is event b. Now somebody told us, okay, what is the probability m is equal to 1? So where is m is equal to 1? M equal to 1 is this. That means max of x comma y should be 1. That's only this cell. Okay, they have no intersection. In the earlier discussion, we said that if there are two events like this a and b which are disjoint, which are mutually exclusive, and they have nothing in common, that means so p of a given b will be equal to 0. Why? Because there is no intersection. So in this case, if you see this directly, the event minimum of x comma y is 2. I have colored that with yellow. So this over here is colored with yellow. So these are the outcomes possible. Then I said, okay, what's the probability m is equal to 1? M is basically max of x and y. So max number should be 1. So that is this event. This yellow and red event has nothing in common. So that means we have 0 probability. Or to directly think it without this, without paint or without the picturize. So if you have to come up with what is the probability that maximum is 1, given that minimum is 2, or given that minimum is 2, so how can the maximum be 1 now? Minimum, at least we have 2. Minimum number is 2. How can we now have maximum number 1? That means 0. So that's also pictorially shown over here. So you have 1 comma 1. We have m is equal to 1. Max number is 1. So in all these yellow cases, we have minimum is 2. Now the second case is, what is the probability that minimum is 2? Given that what is the probability that maximum is 2? Given that minimum is also 2. That means this. So if you see this portion over here, this is the only cell. Only cell that is in this m is equal to 2. Okay, what is the case that if I make all the cells where minimum is 2? So minimum is 2 in this case, minimum is 2 in this case as well. So you have all these cases where minimum is 2. Sorry, where the maximum is 2. Sorry. So in here, these three are the cases. This one, and this one are the three cases where the maximum is 2. Otherwise, the maximum is not 2. Maximum will be more than 2. So now if I have to see, okay, what is the probability that maximum is 2 given that minimum is 2, given that min of xy is 2. So we have this yellow portion and we have this purple portion. We have yellow portion and we have the purple portion. The intersection is only one element. Okay, so the only one element is intersection. And now that is what here. So we have one element in total, and how many are total possible where this, because we are concentrating on b, that is 1 by 5. Okay, this is pictorially saying it, and then if you have to reason, we can also say like this. What is the probability that maximum is 2 given that minimum is 2? Okay, given if minimum is 2, that means there is a possible 2 comma 2. Okay, maximum is 2, will only be there 2 comma 2. So it will be minimum as well as maximum. So this is the only possibility. That's why the probability is 1 comma 5. Earlier, what was the probability? If somebody would have told you, okay, what's the probability of something? What's the probability of event this b? You will calculate it based on this. What the probability of a maximum is 2? You will say this. That is 3 by 16. Earlier probability was 3 by 16. What is the probability of m? Probability of m earlier was probability of m is equal to 1. Probability of m is equal to 1. That is max number is equal to 1. This was not when max is equal to 2, rather was 3 by 16. The probability of max is equal to 1 was 1 by 16. Okay, now this was the prior probabilities. This was our prior probabilities. And somebody given evidence that b happened. Now minimum is 2, we know that. If somebody told me this, minimum is 2, they give me additional knowledge. Probability of m is equal to 1 given b, I have to update these probabilities. So these were my prior probabilities. Probability of m is equal to 3 by 16. I know there will be 3 such rules where maximum number will be 2. Probability m is equal to 1. That means maximum number is 1. There is only one cell. Only one cell, that's this. and this is the probability. This is prior probability. Once I get the new evidence, so I update my belief. Okay, I can do it by probability also. So probability of M intersection B. So that's it. This is completely 0, and in here also probability of M intersection B. Let me write it maybe a bit cleaner. So in here, this is probability of M intersection B divided by probability of B. In both the cases, this is the formula. So in the first case, so we have nothing in common, divide by probability of B, whatever it is, it becomes 0. So in the second case, we have 1 in common, divide by probability of B. So whatever was the probability of B is 1 by this, and then I have to normalize it basically. So I have to come up with probability of A intersection B, the probability of that one element, okay, divided by probability of B. So this comes out to be 1 by 5. So how can you compute the probability of A intersection B? You can say number of favorable events divided by number of total events, and then how can you compute the probability of B? Number of number of f dash, that means favorable events in B, divided by number of total events. That basically you just can count elements. So this cancels down, so you boil down to number of favorable event divided by number of f dash. So number of favorable, how many elements are there in this intersection, and how many elements are there in B. So that's what Parth said. We have total 5, and that is evident from the formula also by using the naive definition of probability. How many of you understood this part? The probability calculation. I'll write it neatly. Probability of A intersection B divided by probability of B. So this can be written as like this: number of elements in A intersection B divided by total elements. Let's call that T, divided by probability of B is number of elements in B divided by total number of elements. Okay, this total got cancelled, so your number of elements in A intersection B divided by number of elements in B. This is under the assumption that everything is equally likely. Okay, that's what we used over here. So probability of this, so we had one element in common, and probability of B, so we had 5 elements in total, so we just divided it. So this is evident from the definition also. Any confusions, any questions on this? Now what we said is, we said probability of an event A given that something happened. So that this assumes that if B happened, we'll concentrate whole probability on this. So I give an example that let's suppose you have a mass, you have some mass 1, okay, and if you have 5 people, you have A, B, C, D, E and F, something of this sort. Okay, let's suppose 6 people are there, and you are distributing a mass of 1. So how can you distribute? Let's give this 0.1, let's give 0.2, 0.1, okay, this is 0.4, let's give this 0.3, or let's say 0.25, 0.25 and 0.1 to this also. So now you have distributed whole of this one mass somewhere. Now if somebody told you, okay, something happened, that means let's suppose this thing happened, this whole thing happened, that means you are removing these two things, you are giving them 0 now, but you have this additional mass, you have this 0.1 and 0.2 additional mass, okay, you have to distribute this to them, but you have to keep the ratio same. Okay, this initially was this ratio, initially whatever the ratio was, you have to keep the final ratio as same, but you have to distribute this in the same fashion. Okay, that's why you normalize it. So I am telling you, P of A intersection B, you see what is the common in both the, if B happened, if some event happened, give that whole probability, give the probability of B, let's assume that to be 1, okay, and then see what the probability of this, and then you can say this is probability of B. So here you are trying to maintain the ratio, and that's why we are calling this normalization. So in normalization, what is happening? You are making sure you're making sure that the probability, the final probability that you have when you reshuffle whole the thing, it's still 1. Okay, and you're making sure of that. And here we'll assume that P of B is greater than 0. Okay, this is not equal to 0. Otherwise, we'll have mathematical inconsistency. But this is what is the meaning of conditional probability, because conditioning means something happened. What is the probability of this? So I told you what is this used for. So you have a prior belief about something. You have prior, and you have to get to some updated probability. You have to update it. So updation rule is this. So this is the updation rule, and we did a couple of examples. Okay, I also told you don't confuse between mutually exclusiveness and independence. We'll come to independence later, but this is the crux we have seen so far, and we did an example also, and you guys answered that as well. Let me again ask you one more question so that you practice more and ask me more questions to clarify it. Question goes like this. You have the deck of cards. You know that there are 52 cards in the deck. The question is like this. What is the probability that both are aces? There are 4 aces. There are 4 types of cards in the deck, and there are 4 aces. Each type of card has an ace. What is the probability both are aces given that one card is ace? Okay, and the second question is, what is the probability? Both are aces. Both are aces. Given that one card is ace of spades. Okay, you have 52 decks and you are giving two cards. You have a hand of two cards. You are basically having two cards now. So you are randomly picking up two cards from the deck of cards, and I am asking you, what is the probability that both the cards are aces, given that one card is ace? And the second thing is, this is the question 1, this is question 2. This is question 1 and question 2. Question 2 is probability both the cards are aces, given that one card is ace of spades. The difference in the question is, in the first question we're assuming any ace. In the second question we're assuming it is ace of spades. Can you calculate the probability? First part, I'll do the first part and then you tell me. So I'll do the first part over here and then you tell me how can you do the second part. So I'm saying probability both are aces. Okay, that means this over here. So this comes out, given that one card is spade. So this is probability both are aces. Okay, and one card is ace. One card is ace, both are aces. That means both are aces. This is equivalent telling you both are aces given one card is ace. Divided by probability one is ace. So here I can tell you probability both cards are aces and one card is ace is equivalent to probability of both are aces. Because if one card is ace and I am assuming second card is also ace, so this is the subset of this. So both are aces divided by probability one is ace. So I am not bringing in symbols. Okay, now let's compute this probability. Okay, let's assume that naive definition of probability. Probability both are aces. Okay, what is the total possible combination? 52 C2. This is the total number of, how can I take out the two cards out of 52?
Yes.
Now both are aces. How many aces are in total there?
4.
So 4C2. This is my favorable case. My favorable case is that 4C2 divided by 52. This is for the upper hand, that upper side numerator. And now one is ace. You can do it different ways. One is ace and one is non-ace. Basically, one is ace. You can break down the problem into, okay, I have two cards, among them one is ace. Okay, and the one easiest way to do it is the complement way. Okay, 1 minus none is ace. Okay, that means 1 minus, if nothing is ace, so basically what I have to do, I have to choose from 48 cards now. 48 C2. Okay, divided by total. This is the answer. And I have written the answer somewhere. Let me check if it is somewhere there. Let me see it. Right. I think this is 1 by 33. This comes out to be 1 by 33. How many of you understood this? So what I said is probability both are aces and one card. This is basically using the definition of conditional probability. Intersection of these things is basically only this one, okay, because both are aces and one is ace is equivalent telling both are aces. Probability both are aces. How to compute the probability? Total number of possibilities 52 C2. That combinations possible from the 52 cards is this. And the favorable events, we have to take 2 aces out of 4 aces, so 4 C2. So this is the numerator. So what about denominator? 1 is ace. So I thought, let's think it in the complement. That means I'll say 1 minus none is ace, no card is ace. So if you have to say, okay, no card is ace, so how can you do that? You have non-ace cards are 48 and 48 choose 2. So 48 choose 2 is the non-ace card. And then total combinations 52 C2. I am saying 1 minus this. So this is my denominator. This thing over here is my denominator. So when you compute these things, it comes out to be 1 by 33. Is it clear?
Yes.
Now can you think about second? The answer goes like this. So you have one card is already ace of spades. Ace of spades. You have to only think of other card. So how many cards are there now? There are 51 cards. Out of them, I have to compute. I have to say the spade. So you have to only compute this, the possibility, the probability of this, because already one is spade. So you have to compute the, okay, what's the probability that this is also an ace? This is of some ace. So 51 C2 total number of combinations, and how many of aces? So one ace, you took out one ace. So how many aces are you now taking?
Sir, can you repeat? Can you just repeat?
So I said I can think of this problem like this. I had two cards like this.
Yes, I have 2 cards.
So one card is already ace of spades.
Yes, one card is already in aces. So
Ace of spades.
I only have to pick one more.
So you have to only choose one more ace.
Yes.
So what's the probability of choosing that one ace out of these 51 cards?
Sir, it would be 3 upon 51.
3 upon 51. So this is I think 3
So
upon
1 by
51.
17.
So this was 1 upon 1 by 3, the 1 by 17.
And
So we have
Mhm.
1 by 33 and we have 1 by 17. This was probability in the first case, this is probability in the second case. This is almost double. Second time we have almost double probability. How? Why? How many of you at least are astonished? Oh my god, there is something going on here. Both cards are aces. Given one card is ace. Both cards are aces, given one card is ace of spades. By just adding one more thing, almost probability shifted and it almost got doubled. What I told you in the first case, you were saying that both the probability both are aces given that one is ace. Okay, in the second case, you were saying both are aces given that one is ace of spades. So I am claiming that in the second scenario, I am giving you more information. How? So in the first case, I am saying there is an ace. It can be any possible ace from the 4 aces. Okay, in the second case, I am giving you concrete information that it is an ace and from the spades. I am basically decreasing uncertainty in your case. Okay, so decreasing uncertainty means it should shoot up probability. That's what is happening. So initially we had 1 by 33, then it shot up to 1 by 17. So it from 1 by 33 it went to 1 by 17. Okay, just by giving additional information that I decrease your uncertainty. Initially I said there is an ace and you were like there are 4 aces, I don't know which ace it is, but now I gave you that there is an ace, it is ace of spades. I decrease the uncertainty. If I decrease the uncertainty, it should mean that probability should get increased. So you can see that probability also got increased. As I gave an example also, it is like solving a case. If you are in the crime scene, so if there are 2 people A and B who are potential who are the potential for this crime, they have committed the crime. So if I say I found a gloves, so this is an information, this is an evidence. But if I say I found a gloves, it belongs to person A, because now this is more evidence. I just did not find gloves only. I also gave you one more information. Now the uncertainty, as uncertainty decreases, your probability you should be getting more certain. You should somehow be more certain. Okay, what should happen now? So in the similar case, you can see over here that that's what happened. Here both are aces. Given one was ace, less information. Both are aces. Given one is ace of spade, you are given more information. That's why now you should be more certain that because your uncertainty was decreased. Okay, you should be now more certain. Okay, I hope that this thing at least is somehow blowing a sense into you that how counterintuitive probability can be, and you have to sometimes think harder. You have to sometimes think in different ways to land the answer. Okay, so how to basically solve these? So this is a good discussion to have right at this point. How to solve problem? How to solve a problem? The first way to solve a problem is to break it down. Break down the problem. You have to break down the problem into smaller chunks, and you assume that these smaller chunks are easy to solve. Okay, this I can also prove with probability, by the way. So let's suppose I have to somehow compute probability of this, probability of event B, somehow like this. This is my sample space, and this is my sample space, and this is my problem that I have to solve, probability of B. So what I said is, I said break down the problem. So you break down the problem in such a way so that the smaller portions are easy to solve. Let's suppose I'll break down the problem like this. I'll break it down like this: A1, A2, A3, A4, A5, something like this. A1, A2, A3, A4, A5, A6. So I had a problem. I broke down the problem. So I said, okay, now the question is, I have to solve this probability of B. So what will I solve actually? So I'll solve like this. I'll say, let's solve it like this: probability of A1 intersection B plus probability of A2 intersection B, because I know that these are disjoint, so I can add them, and so on, plus probability of A6 intersection B, something of this sort. Okay, now here I can break this down. Let's suppose I can also from multiplying rule I can do this. So the assumption here is these sub problems are easy to solve. Sub problems are easy to solve. This is a general thing. So how to solve these problems? Break them down into smaller problems and see that if you can solve the sub problem, and then you can put them together. This also works in if you are solving any other type of problem. Okay, this is one thing that you have to keep, you have to do in the probability. And one more thing that I'll tell you: bring in notations. Bring in notations, because somehow our brain is trained to do this algebra. Then let's suppose if I give you algebra 4 plus 5 plus something like this, So you will do it quite easily and quite quickly. But if I give you a mathematical problem, you have 4 bananas, 6 apples, this chips and that, and then I'll tell you to compute something, it becomes pretty hard for us to do that. So it is good to bring in the notations. And then let's suppose usually what I do is I have a problem, I'll say AI denotes this, E denotes this, A denotes this. So bring in those problems so that to boil down into the notations, and then you play with the notations, because it's for our brain quite easy to perform algebra notations. So when you perform the algebra, it becomes really easy. This is how you should solve problems generally in probability or in general in life. If you are having a problem, try to break it down and then assume, not just assume, make sure that the smaller subtasks or sub problems are easy to solve. And second thing, whenever you are doing a problem where you are needed to use mathematics, so bring in the notation and try to formulate your problem so that you bring it mathematically, and then you can use the tools of mathematics like algebra or other tools that you are learning here, so that you can do the problem easily. So it's easy for you to now do the things by using formula. If I say probability of A given B, you now easily know this probability of A intersection B divided by probability of B. So everything has a physical meaning. Everything among this has a physical meaning, but it becomes easy for us to just manipulate these symbols, and numbers. So I could have said it like this: probability of, I will have named an event, that event will be huge, and given that this event happened is equal probability this and this will happen simultaneously divided by probability of this. So this will become too much clutter and too much verbose, and our brains are not good at performing these operations if given verbose things. So it is better to bring in notations and formalize the problem and then use the tools of mathematics. Any questions so far? Okay, let's have a brief discussion on where is conditional probability used. So you know that this is where we'll use it, and at least have a notion how to use it. And the first generic statement I'll make is because in machine learning, deep learning, you are trying to find parameters. Okay, if you have a model, and in that model you have to find a parameter. So basically what are you doing is you are saying probability of this probability of parameters given data. You are given some data and you are finding the probability of these parameters. This is an iterative approach. Why is it an iterative approach? Because each data point is an evidence. Okay, and you are tuning the parameters. Like you are saying probability of these parameters given this data point. Let's suppose given this data from, let's suppose, 1 to 10. Let's suppose we have batch size of 10. Probability of these parameters, the parameters I have given this data. So you compute this, and then you see, oh, it does not match up with the reality. Okay, let's use an iterative approach. Let's change the parameter. So I am changing the parameter, again computing probability of the new parameters given this data, and you keep on doing it iteratively, and you are thinking that I will increase the probability. Probability of these parameters given the data, it will be more than. Okay, you want to compute this basically. So this is the generic framework. So you are computing parameters given your data. So data is your evidence, and the parameters are the things that you want to learn. The first thing is in the classification algorithm. In the naive Bayes classifier, we'll use Bayes theorem. So whatever we studied today, we'll use this in some other format in which we'll derive the Bayes theorem first, and then we'll use the Bayes theorem. So in that you have conditional probability. You basically have probability, let's suppose, of email being a spam given these features. Probability of spam given features. Okay, and then you say that this probability is equal to probability of features given that this is spam multiplied by this, and you basically use the Bayes theorem over here. So use Bayes theorem. But why is this called naive Bayes? Because we make a naive assumption there. That's why it's called naive Bayes there. Okay, you can use it for spam filtering. You can use it for classification of different things. And then coming to generative models. This was for the classification. Okay, then coming to generative models. So in generative models, usually you compute the joint probability. Okay, by joint probability, I mean you are saying the probability of x comma y. You are saying this probability of this and this. Okay, let's suppose in GANs. So there is a generator. Generator learns probability of x given this z. So where z is some latent variable. Okay, and the discriminator basically learns from the real data probability, and then it tries to generate from this data probability of, these are my latent variables, probability of x given this latent variable. And then discriminator learns distinguish between the real data. The real data is basically p of x. Okay, and then you can generate a lot of things, and we'll go in detail, but I'll just show you that all of these things are basically what I can say conditional probability based. And even in the sequence modeling, you are saying probability of a word, of the next word, given I have this context, given I have w1, w2, w3, I have this context. This is called context what is the probability that next word will be this? So you are again conditioning. Okay, what are you conditioning on? You are conditioning on the context. Probability of next word, next token to be this, given I have this context. Okay, and this is in the language models, and in GPT, RNN, we do same stuff like this. Even in the hidden Markov models, many of you might be working in speech, so that people are a lot of using this hidden Markov model. So there also you have to have transition probability, emission probabilities, and you have to see, okay, how, and then you may make an assumption that the next state is only depend on the previous state. You make this assumption. That's why they're called Markov models. Okay, again, you are using this in generative models, in hidden Markov models. So here I talked about language models. In this, transformers are using it, RNs use it. Okay, LSTMs use it, hidden Markov models use it. Then you have a whole set of neural networks called Bayesian neural networks. Okay, there you use it for uncertainty estimation. So you have Bayesian neural networks. So there you use it, and then in the reinforcement learning. So in that, what we do is we basically call it as an MD process. This is Markov decision process. So again, this is the probability of this state, probability of, let's suppose, state t plus 1 given the state t, and I am performing this action. So you basically come with the policies. So in policy, they're all probabilistic in there. If you use, if you let's suppose use these reinforcement learning in the generative AI, you can also see it in variational autoencoders. There also you say the probability of y given x comma z, something of this sort. In the diffusion model, you still see the same thing. Okay, you are saying probability of these features given this. So all of these things. So even in animated, I have written a lot of these things. I'll share it later. But if you see more or less this conditional probability, okay, because I told you this is a thing on base of which you have prior and you update the belief. You update the probability, and it gives you those updation rules. It is used almost everywhere in deep learning. And we have probabilistic algorithms separately, so that it is heavily used. So we're discussing about conditional probability. The one formula that we wrote is that we have probability of an event A given that B happened. So once B happened, we have to update the probability. So if we call probability of A, this is prior. So we had some prior knowledge, okay, some prior belief. So a measure of belief is also a probability. So we have this prior, and then by the help of this conditional probability, we update this. So we have to update our probability, and we get some evidence based on which we update it. And once we get that evidence, we update the belief by using the formula of conditional probability. So what is conditional probability saying is that you take the intersection of A and B and see what's the probability of that, and you normalize it by the probability of B, and here make sure that this probability of B is greater than 0. This is what we saw. Okay, this is the one formula that you should remember, and do not try to memorize it, but you should learn it to derive from the first principles. Probability A given B is probability of intersection of both of these events divided by the probability of B. This we do because of the intersection. This we do because we only give the probability of the intersection part, removing all the other components. Okay, and this is our prior, and then we update it to get this value. Okay, let's do some more examples. I'll give an easy example so that you will again reason it from the first principles. We have done a couple of examples in the last session, so we'll do more examples so that you get at least a firm foundation, so that you believe that you understand this topic. The question is like this: a coin is flipped twice. So we have a coin that's flipped twice. A coin is flipped twice. Now you know that there are four possible outcomes. Sample space contains 4 possible outcomes that you already know. Let's assume that they're equally likely. So equally likely. I'll just highlight the key terms. I'll not write the whole question so that it will save me time also. So coin is flipped twice. Now the sample space, you know, contains 4 elements, and now I am assuming that all of the outcomes in that sample space are equally likely. Okay. So now the question goes like this: what is the conditional probability? Both the flips landed head. So both flips land at head, because we are flipping the coin twice. So both flips landed head given that. Now this is given information. So we are now in conditional probability. Given the first thing is at least, let's suppose A is and B. I'll say 2 things. So A, one of them is head, one of the flips is head. Okay, and the B is let's say the first flip is head. Let's consider this. The first flip is head. We have done pretty similar question on the card decks, which was maybe a little bit complex than this. You should be now easily able to do this, and then you also can think a lot. You will see that these questions might look similar, but the answers they give are quite different. Okay, I'll pause here for a second. Can you please solve it and answer? Okay, so I'll summarize the question again. So we have a coin, and a coin is flipped twice. So this coin is flipped twice. So we have coin and this flipped twice. Now what we can get is we can get head, we can get head and head, we can get head and tail, we can get tail and head, we can get tail. These are the 4 possible outcomes that we have. So all of the 4 outcomes that I wrote, they are equally likely. Okay, then the thing is we have an event. We have to find the probability of both flips landed head. This is the probability that you have to find. The probability of this you have to find. And now I am giving you conditional. Given that one of the flips is head, and in the second case, first flip is head. Okay, given one of the flips is head and the first flip is head, you have to compute the probability of this. You have to compute 2 probabilities. Probability both the flips are head. Okay, given one flip is head, and in the second case, first flip is head. You have to compute the probability. I assume now you understood the question. Okay, let's solve it stepwise. We'll see. The first thing I said is, in order to solve such problems, bring in some notations, because it becomes easy once you bring in notations. Then your brain can do computations on it. It becomes easy to perform algebra or any other mathematical operations on it. So we'll say call this event, let's suppose call this event A or B. So we'll say B is when both the flips landed head. Okay, so B is that event. Let's call these things events A and this also event A, because we'll solve them separately. So now we have brought in the notation. So we have to compute probability of B given A. So B basically denotes this, both flips landed head. Probability both flips landed head A. One of the flip is head, that means at least one is head. Okay, so what is the probability? You know the formulation. Okay, we'll go by the formulation, we'll go to the first principles as well. The formulation goes like this: probability B and A, this intersection, if I'm putting comma as my intersection, divided by probability of A. Okay, now this says both flips land at head. This says one of them is head. Okay, so one of them is head. So what is the intersection in both? So both flips land head is head, because we have this. This is our sample space: head tail, tail head, head head, tail tail. So this is our sample space. These 4 are our sample space. Now I am saying A event happened. At least one is head. One of the flip is head. So one of the flip is head basically means these 3 things, because we have head tail, tail head, head head. So these are 3 things that says this event happened. Now this event happened. Okay, and then we have this B. So B is 2 heads appear. So that means this portion, this one. Okay, now you see what is the intersection of both of these. So intersection of both of these is this probability of head head. So intersection is basically probability of head comma head divided by what is the probability of A. Probability of A that you saw, A is at least one head. This is the probability. Probability of A basically means probability of head tail, tail head, tail tail. Okay, now you know what is the probability of this. Each are equally likely. So what is the probability of this? So this is 1 by 4. What is the probability of this? Because there are 3 events. This is 3 by 4. So this is 1 divided by 3. Okay, everybody agrees on this? Okay, so we saw it here like this. We also wrote the formula and we also did it with the first principles. You can make a sample space and then you take it. It's basically like this. Initially the probability was 1 by 4 for each of these elements. 1 by 4, 1 by 4, 1 by 4 and 1 by 4. Each of the element had probability this much. Now once this happened, so that means this thing has happened now. This thing happened. Okay, so now this got probability 0. Initially it had 1 by 4. Now we have to normalize the probability. We have to give all the probability 1 to these 3 events. So initially it was 1 by 4, 1 by 4, 1 by 4, 1 by 4. One of them became 0. Last event, let's suppose, you have to cut it down. Now you have to distribute this. So how can you distribute it? You can say 1 divided by 4, 1 by 4, 1 by 4 divided by 1 by 4 plus 1 by 4 plus 1 by 4. Each of this should be done like this. So I'll write it here. So 1 by 4 divided by 1, that is 3 by 4. So I'm writing it because I'm dividing by whole of the event, whole of the A. I'm normalizing each of this. So this thing now goes to 1 by 3. Okay, so each of this will get 1 by 3. This will also get 1 by 3. This will now get 1 by 3. Okay, this is what they'll get. Now I'm thinking, okay, what is the probability of B? The probability of B given A, only intersection is this part. So its probability is 1 by 3. That's what I wrote over here. So I showed you two ways of doing it. Directly by using the formulation, you can see intersection and this. Otherwise, you can use first principles. I had this sample space. I'll restrict. Then I'll reshuffle probabilities. Even now, if I am asked to compute probability of some other thing, okay, I can also use these things. That's why I said do not memorize these formulas. Do not memorize them. Otherwise, you'll again fall into that pitfall where you will use the mechanical ways. Okay, probability of B of A is intersection of this. So it is better to go in this as an approach also. Do not remember the formulas. You should be able to derive them. So okay, I hope with this example it got a bit more clear. Now the intuition that Arshan said was quite good, because that's what my goal was. My goal was to teach you thinking. So Arshan said this question somehow, this like first flip is head, and he didn't calculate it. He said approximately it should be 1 by 2. It should be greater than this. The rationale he had is because we have more information here now. Yesterday I said if you have some more information, you get less uncertain. So okay, you increase or decrease the probability accordingly. So here initially it was only one flip is head. One of it can be first flip or it can be the second flip. So here I said first flip is, I gave more information about this. So but natural, if this probability is 1 by 3, so this should be a little bit higher than 1 by 3. So he guessed it to be 1 by 2, and 1 by 2 came out to be the right guess. Okay, but let's see now how to do this also. Okay, so again we'll have to compute probability of B given A. Probability both are heads, given first flip is an head. Okay, so if you directly make first flip as head, okay, directly, now here there are two possibilities. It's very easy to solve intuitively. So first flip somehow is fixed head. So now you have the second flip. Second flip can be either head or tail. Okay, so there are two possibilities here. Okay, there are two possible, either head or tail. Okay, so what is feasible for us? Head. It should be head. So 1 by 2. There are two possibilities. It can be head or it can be tail. Okay, because one first flip is sort of fixed. Now we are saying that it is 1 by 2 then. Okay, this is quite intuitive answer, but let's solve it by using the probability. So we can write it like this: probability of B intersection of A divided by probability of B. We'll again do it from first principle and with the formula. So probability both are heads, probably first flip is head. So what is the intersection in both of these? Okay, probability of intersection of these. Both are heads, that means head and head. Okay, the first flip is head. The first flip is head and head tail. So this is our event B and this is our event A. So if you see intersection in both of these, that's probability of head, and this is the intersection. This is the intersection, head and head. So I can write it over here. I can write probability of head comma head divided by probability of B. Probability of B. What is probability of B? Head and head. This is probability, and there are two heads. Sorry, probability. This should be A. Sorry, probability of A, because we have to normalize. This is probability of A. Yes, I have written correctly. So over here now we have three events. You know, this is for the probability of A basically means the first flip is head. So this is head tail, and this is head head. Okay, I think these are two things possible. So you know that all things are equally likely. Probability of head and head is 1 by 4, and this is 2 by 4, and this is 1 by 2. Okay, not a pretty big deal. So we derived it from the formula. This is a mechanical method which I hate. Why do I hate it? Because it usually abstracts details, but it gives the correct answer. So how to now reason it from first principle? So you can do it like this. So we have these four possibilities: head head, head tail, tail head, and tail tail. Okay, these are the possibilities. Now somebody told me that A happened, this A happened. If A already happened, so that means I have to restrict my possibilities to the world of A. This was my sample space initially, and everything was equally likely, 1 by 4 outcome. Now I have to restrict my possibilities to A only. So what is A? The first flip is head. The first flip is head. The first flip is head. So this is my world now. This is my world. Okay, that means this and this got probability 0. Okay, I had to reshuffle probability. Initially the probability was 1 by 4 for everything. So you can see now, in order to respect the axioms of probability, this event will have probability 1 by 2. This event will have probability 1 by 2. Initially they had 1 by 4. The evidence I got, I had to update the belief. How could I update mathematically? I would have said initially it had 1 by 4. So I'll say 1 by 4 divided by, it had 1 by 4, this is 1 by 4. So 1 by 4 plus 1 by 4, that's 2 divided by 2 by 4. So 1 by 2 for 1 by 2 for this also. Okay. And now if somebody tells me, find the probability of B given A. Now B is this portion only. B is this portion, because red already happened. B is this. So what is the probability? It's 1 by 2. Directly from this you can see it is 1 by 2 directly. So, and one more thing that I mentioned, I again mentioned that you can see it over here. So one flip is head, it gave 1 by 3. First flip is head, it gave 1 by 2. This looks somehow counterintuitive. One flip, or how does it make sense? But yesterday we had discussion that here there is an additional evidence that here we are making the information more certain. We are saying it's not just a flip now. So I'm giving additional information that the first flip is head. Okay, I hope that you understood this. Any questions on this? Let's do another question on this conditional probability. Okay, the question goes like this. I'll read the question from here. A student is taking a 1 hour exam. Okay, so there is an exam which student is taking. It has a limit of 1 hour. You can use 1 hour to complete the writing of the answers. Suppose the probability that student will finish the exam in less than x hours is x by 2. Okay, so there is an exam which is total of 1 hour. The probability that student will finish the exam in x hours or in because hours can now be 0 to 1. This can be hour. So 0.5 means half an hour. It will take half an hour with the probability. 0.5 divided by 2 with this probability. It will finish the exam with this probability in half an hour. So this x, so I am saying the probability that student will finish the exam in less than x hours is x by 2, and x should have value between 0 and 1. Okay, I'll just circulate like this. Then you have to tell me, given the student is still working at 0.75 hours, the student will notice that he is still working at 0.75 hours. So what is the conditional probability that he'll use the full hour? He'll use full hour. Pretty tedious question to understand. I'll simplify it again. So you are a student in a classroom and you are giving an exam. The exam duration is 1 hour. Okay. The probability that the student or you will finish the exam in x hours is x by 2. Okay. So x goes from this. So I give an example. Let's suppose if you are taking assuming that okay, I'll take 30 minutes, you will take 30 minutes with this probability 0.5 divided by 2 will take with this probability. If you are saying I'll take full 1 hour, so that will take with probability 1 by 2. Okay, because you're just filling the values of x. Now something happened. What happened? Somebody saw the student and he saw that student is still writing at 0.75. So at 45 minutes, student is still writing the exam. So now the question is, what is the probability that student will use full hour? What is the probability that student will use full 1 hour? Now if you understood the question, so the question that was given is like this. This was the question. So now let's first bring in the notations. So we have to find the probability that student will use full hour. Student uses 1 hour. So we said, let's say student uses full hour, consider it, let's suppose f. So he uses full hour. This is f means full. So here we'll bring in a notation for the 0.75. The probability, let's consider probability Lx. So this means student finishes within x hours. Okay, student finishes within x hours. This is what I'm bringing one more notation. Now I have to find probability that student uses full hour given that student is still writing at 0.75. So but this means student finishes within 7 hours. I have to take its complement. If a student is still writing at 0.75 hours, I have brought a notation that student is finishing within x hours in Lx. So if I take its complement, that means student has not finished. That means he is still writing at 0.75 hours. Basically, I have to find this. Okay. Now this is equal to probability of f comma L 0.75 complement divided by probability of L 0.75 complement. Okay, this is by conditional probability. If you see the intersection over here, so we have a full hour, so we have to use full hour, and student is still writing at 0.75. So student has a full hour and he is still writing at 0.75 hours. 0.75 hours. That means the intersection part is 1 hour. Okay, because he still is writing at 0.75 hours. The intersection basically means, so he might take full hour. So the intersection is full hour. So we can write probability of full hour over here divided by. So probability of this, probability student is still writing at 0.75. But what we can compute is, we can compute student has finished before some x hour. So we can write it 1 minus student has finished at 0.75. And we know how to compute this, because in the question it gives that given that student student can finish the exam within x hour is x by 2. So we'll compute it easily now. So P of f, this basically means probability that he'll utilize full hour. Okay, so that is 0.5. How 0.5? Because 1 by 2. If he uses x hours, so it's x by 2. So x hours basically means 1 by 2. So this is 0.5, and 1 minus L 0.75. This basically means 0.75 divided by 2. So once you compute it, it comes out to be 0.8. Okay, I'll again sort of summarize this question. Once we had the question, the first thing we brought in these notations. So once we brought the notations, and then we saw something happened. So this thing happened, and we had to also write in some other fashion. So you can bring in notations in your own way. So this is the easiest way to bring in the notation. Sometimes if you bring some tedious notation, you have to think harder. So decide on what notation you have to bring in, so that it makes the thinking easier. So once you brought the notations, then you directly use the formula of conditional probability, and you will end up with this answer. Okay, I hope you understood this question as well. Let's move on to the next question. Question goes like this. So in a card game, there are 4 players. So in a card game, we have 4 players. So we have 52 cards. So yesterday I showed you there are 4 types of these cards. Okay, each have 13 cards. 13. So we have something of this sort. So this is called as spade. Then we have something of this which is called as diamond. And then we have something like this which is called hearts. Okay, then we have something like this. This is called a club. So we have 4 types of cards in a 52 card deck. So 4 players are playing, and each is given 13 cards randomly, and it's well shuffled. So all of these players are given. So we have players, let's suppose A, B, C and D, something like this, and each of the players is given 13 cards. Okay, now given in the question is that if the C and D, if they have got 8 spades, okay, now you know that this spades. So spades are there are 13 spades. Now 8 of these spades are with C and D. Now we have to compute what is the probability that A has 3 among those 5 remaining spades. 3 among 5 remaining spades. Again, to summarize the question, we have a deck of cards which contain 52 cards, and we have 4 players. We are basically drawing these cards. We are giving 13 cards to each of these players, and now given that the C and D, they have 8 spade cards. Out of these 13, they have already got 8 spade cards. So now I have to find the probability. What is the probability that 3 among the rest of the spades, because now we are left with 5 spades. Total are 13 spades, 8 are given to C and D. Now we have 5 remaining spades. So what is the probability that 3 among those 5 spade cards are with A? So here if you see, so we have A, B, C and D. C and D got 8 spades. Okay, total spades were 13. That is, we are left with 5 spades. So 5 spades are in the other cards. So we have to give 3 cards. The favorable event basically is we have to give 3 cards out of these 5 cards that are of spades. So what I can write is I can work with the reduced sample space. I can work with a reduced sample space. So how to work with that? So initially I had 52 cards. So out of that I had 26 which were given to C and D. 26 cards were given to C and D. And out of these I know that we had 8 spades. Okay. Now other 26 cards, they are to be given to A and B. Now because we have 13 spade cards in total, so 8 cards are given to C and D. So we are left with 5 spade cards, 5 spades here. Now I have to compute probability. A will get 3 spades out of 5. A will get 3 spades out of 5. Given that C and D has got 8 spades, 8 spades out of 13. Okay. So what I am saying, I am reduced sample space. So what do I mean by reduction? So now I will work with this only. I am saying I am left with 26 cards because somehow this is settled for me. This is given information. So I will remove this. I am only concerning with this. So I have now 26 cards. So out of 26, I have to give 13 cards to A, because I have to compute probability A will get 3 spades out of 5. So I have to actually give 13 cards to A. The total possibilities are 26, 13. So these many number of combinations can be given to the A. Okay. Now what are favorable outcomes? Favorable is that we want to give it 3 cards out of 5 spades. So 5 out of 3. Okay. Now he got 3 cards. So basically what we basically want is we have to give it more than 10 more cards. But out of how many? We initially had 26. 5 were spades. So 5 out of 3 and 21 out of 10. So this is the answer. So the answer is 0.339. Okay. So with these examples, we'll now move on to the some different theorems on this conditional probability. I hope that once you revise these and once you do more problems, this will become more intuitive and you will have a different method. So again, the first thing is what you should do is you should test. So whenever there's a problem, so I'm saying whenever there's a problem, how to solve that? How to solve that? How to solve that? Think of the possible outcomes, see sample space, and can you do something with the sample space? Can you do with some permutation combinations? And try with easy cases, easy and extreme cases. Take a small example. If I am giving you some example, take an example and try to fit in. Let's suppose if I am making a generic statement, try in to bring a simple example and see it for that. If I say, let's suppose there are n people, out of n people we are choosing k people, so you can do like this. Let's suppose we have 10 people, and let's say we'll take 2 out of them. Make an example, use an example, and this might be an easy example. Then do it in an extreme example, so as to get some sense out of the problem. Okay, try easy and extreme cases first. So at least get a notion of the problem, because every problem won't be solved directly, and you will not find solutions on the internet either. So let's suppose if you are now at a situation where you have to solve a probability problem. First thing is, if it's a generic problem, try to bring it in down and use some cases, but use some easy case and then some extreme cases to get the notion. And the second thing that I said yesterday also, break the problem down. Break down the problem into chunks. Into smaller subproblems. Assuming that when you are breaking the problem into smaller subproblems are easier to solve than the problem, and then you can just put that thing together. I took an example like this. I said, let's suppose this is an event B. So if you have to compute the probability of this B happening, so what you can do is you will break the whole sample space like this. This will be A1, A2, A3, A4, A5, something like this. And then if you have to compute probability of B, you say probability of B is probability of AI intersection B. So where I goes from 1 to 5 in this case. So you will summation, and we are assuming that to solve the probability of this is easy. To solve the probability each of this is easy. Okay, this is the general notion. Okay, I have given you a lot of perspectives how we can solve problem. Let's move on to theorems. It's a pretty easy thing. So if we saw probability of A given B is equal to probability of A and B divided by probability of B. Okay, that this is what we saw. Probability of B should be greater than 0. This is what we saw, the definition of conditional probability. And now if I see this, so if I just shuffle it, if I say probability of A and B, this is equal to probability of B multiplied by probability of A given B. Okay, something of this. I just took it from this side. I multiplied by P by B on both sides. So multiplied it here, multiplied it here. That's what I got. So this thing over here is called multiplicative law. So multiplicative rule or law. So this is theorem 1. Call it theorem 1. So this also can be written like this. Probability of A comma B is equal to this. This can also be, I could have written it like this. Probability of A comma B is equal to probability of A happening multiplied by probability. Now A has happened. Now what's the probability of B? So I told you multiple times, try to read these equations as English. So how can I read this as English? Probability that an event B happened. What is the probability of A happening? Probability of A given that B happened. This is probability of A and B happening simultaneously divided by the probability of B. So in this case, probability of A comma B, how I can read it? Probability A happened. Now A has happened. Probability of A. Now I'll write it first. Probability A happened. This is given now. What's the probability of B? So these things are quite like easy to come up from this formula. Okay. So this is theorem 1. I can extend it. So if I have something like this, probability of E1, E2, and so on till En. What I can say is I'll say probability of E1 multiplied by probability of E2 given E1 happened. Okay, and multiply. I'll keep on basically multiplying. So I'll just use this multiplier, and you can prove it by induction, by the way. But there is no need to prove it by induction, so you can directly even see it by examples. But if you want to use induction, you can also do that. So here what I'm saying is probability E1 happened first. Okay, then I'm saying multiply by probability E1 happened. What's the probability of E2? Now E2 happened, so we can write probability of E3 given E1 and E2 happened multiplied by probability of E4 given these 3 events happened. Now E3, E2 and E1 happened, and so on. Okay, you can keep on going like this. So this is the generic form of this multiplicative rule, multiplication rule. Probability of E1, E2, E3 till En happening is probability E1 happened. Then once you have this probability of E1, basically this now happened. Okay, now you will write it in this happened part. Given that now you have a probability of E2 given that E1. So once you wrote this, so here you assume that now E2 happened. So once E2 happened, so you will write it in this probability E1 and E2 happened. The probability of E3. Once you wrote this, so probability E3 happened. Now E3, E2 and E1 happened. Probability of this. Okay, this is called as multiplication rule or multiplicative rule. This is the generic form of this. Okay, so what we wrote so far is probability of A given B is equal to probability of A and B divided by probability of B, or This is also equal to probability of A comma B divided by probability of, so I'll write it in inverse, probability of A comma B divided by probability of A is equal to probability of B given A. Okay, so these are two things, and here probability of B is greater than 0, here probability of A is greater than 0. So this is by the definition of conditional probability. So from here I can write probability of A and B is equal to probability of A given B multiplied by probability of B, or probability of A given B multiplied by probability of A. This over here is a multiplicative theorem for two events, so then I also wrote the generalized one. So this over here is the conditional probability. So this is conditional probability, and this over here is multiplication rule. So for two events, then you saw the generalized one also. Okay, now from this I can do one more thing. I can come up with the Bayes rule. I think this P of A is not visible. Let's make it visible. Dot, this is dot P of A. I think rest is visible. This brace is not visible. P of B given A. Okay, so now if I have to come up with a Bayes rule, so what I can do is pretty easy. Basically Bayes rule is something of this sort. So A comma B and probability of B given A. So you can see these two things are quite different. Probability, B is given, probability of A you have to find. Probability A is given or A happened, and you have to somehow connect these things. You have to connect them. So you connect these things by Bayes theorem. How can you connect? It's a one-step procedure. So over here, if you see probability of this is this, you now know that probability of A comma B multiplied by probability of B is equal to probability of A comma B multiplied by probability of A. Okay, now pretty easy. If you have to, this was equal to, this is probability of A given, sorry, this is B given A. The probability of A given B, the probability of A given B, probability of B given A. So this is from this. So if you see this part over here, I just wrote it like this over here. Okay, so what I can now do is I can just reshuffle these terms. I can come up with this probability of A given B is equal to probability of B given A multiplied by probability of A divided by probability of B. So this over here is Bayes theorem. Pretty easy to derive from whatever we saw. So we saw at least couple of theorems. The first theorem we saw is this multiplicative rule, and then the second thing that we saw is generalized form, and the third thing we saw is Bayes theorem. Pretty much easy to derive, and we did not use any intuition, just the mathematical notion. We just shifted terms here and there, and we came up with this result. Everybody fine with this so far? The algebra we did, I have not explained to you anything so far. Everybody sort of understood the algebra we did on this. So if you see this now, so this is called Bayes theorem now. So it is doing what? It is relating these two things. So we have, I think, this and this. It is relating these two things with some formula. Okay, that's what I said is Bayes theorem. So now I'll tell you the profound of this Bayes. I'll tell you how profound this Bayes theorem, how deep this Bayes theorem actually is. Okay, now we will dissect it down. Okay, you might remember the problem that I introduced in the initial lectures by Daniel Kahneman. So in that example, I said I give you a description. I gave a description of a person. Then I asked you how likely is this person going to be a librarian or a farmer. In that, most of the people initially said it resembles library because there were certain words which resemble, okay, this should be a librarian. Then I told you, you missed a lot of information. You missed the prior. Okay, the prior was basically how many librarians are there actually. So let's consider an example. Let's consider we have a ratio of 1:20. 1:20 to the librarian to the farmers. Librarian and farmers. This is the ratio. Okay, we have 20 farmers and 1 librarian. This is the ratio. This is the prior belief that we had. Okay. Now the description, if it fits, the description that was given, if it fits 40% of the librarians, and it only fits, let's suppose, say 10% of these farmers. So that means, let's take it like this. So that means 10 is to 200. So we can take this ratio, 10 is to 200. So these many farmers and these many librarians. So if the description I gave you, it looked more of a librarian. Okay. So if we now believe in this prior, we said, okay, prior belief is this. So there are 10 librarians and there are 200 farmers. This is the ratio. So if it fits the 40% of the description, so this 40%, so 40% of this is 4. These are 4 people. So if this over here fits only 10% of the people, so if this over here only fits 10% of the people, so 10% means 20. Okay. So now you see, even if the description fits almost 4 times more, okay, then what still you have? If somebody says, what is the probability? What is the probability of person being librarian given the description? Okay, so what did I say? I'll make it a little bit pictorial. So we had something like this. So we had these many people. Okay, we had people like this. And in people, I'll make a diagram like this. So here these many were the farmers. Let's suppose 200 farmers were there. And we had 10 librarians. So when I gave the description, so based on description, you said, okay, it seems that it is more likely to be a librarian. So I'll say, okay, can you quantify this? So you can say, it looks that 40% of this description, we can assume that it fits to the 40% of the farmer, 40% of librarian, and maybe very less likely to be a farmer. That's maybe 10% of the farmers. I said, okay, the 40% basically means this much. Let's consider this pictorially this much, say till here. This is 10 librarians, so 40% basically means 4, so this many. Okay, this is 40%. And farmers are 10%. So how many of 10%? Let's consider this 10% over here. This is 10% of the farmers. Pretty bad at drawing, so let's write it better manner. So this over here, if you see, these many farmers. So how many farmers are there? So farmers we saw is 20 because 10%. So 10% basically means 20 farmers, and 40% here means 4 librarians. So we took the description that was given. Let's suppose it assumes to be true for 40%. So that's we got the 4 numbers. The probability that the person is a librarian given the description. So what is the probability now? So you can see out of these total. So we have 4 librarians. How many total people were there? 4 plus 20. That is 4 by 24. These many total that fit the description. 20 farmers fit the description and 4 librarians fit the description. And favorable events were 4. So I think this comes out to be 16%. This is quite counterintuitive. But we took, this was our prior knowledge. So how many of you understood this example now? If you understood this example, you understood Bayes theorem.
But मैं सर ये बोल रहा हूँ कि ये जो आप बोल रहे हैं ना, this description fits for 40%. Where we get this?
So this thing over here, जब मैं बोल रहा हूँ ना, this one fits to the 40% library. This means that when we saw the evidence, we thought, okay, this evidence is more likely to be a librarian than a farmer. So let's have a ratio of 4:1. It fits 4 times more to the librarians than to the farmers. I said, okay, 40% to the librarians, 10% to the farmers. That's a quite logical assumption. Okay, because we saw that description fits more to the librarians. Yes.
सर मैं जैसे समझ गया हूँ, let me correct me if I am wrong. पहले हमें prior belief है that is 1:20.
Yes.
That's the ratio
Yes.
of okay. फिर उसके बाद हमें एक एविडेंस मिल गई, हमें एक डिस्क्रिप्शन दिया गया, वो हमें एविडेंस मिल गई, तो फिर ऑन द बेसिस ऑफ दैट डिस्क्रिप्शन वी आर अज्यूमिंग समथिंग कि ऐसा होगा, राइट?
यस इन दिस केस वी आर अज्यूमिंग दिस. तो डिस्क्रिप्शन के बेसिस पे हमने अज्यूम कर दिया, एंड दिस अजम्पशन इज क्वाइट लॉजिकल एंड कोहेरेंट. किस को लग रहा है अजम्पशन ठीक है कि मैं बोल रहा हूँ कि ज्यादा ये डिस्क्रिप्शन फिट बैठ रहा है लाइब्रेरियंस पे. आई एम सेइंग कि 4:1 है कि 4 लाइब्रेरियंस और 1 फार्मर पे ये बैठ रहा है, यानी 40% इन पे और 1 इन पे, यानी इन पे 10%. एंड देन आई एम मेकिंग द कैलकुलेशंस. So if you now understood this, you understood the heart of Bayes theorem. Okay, let me tell you how is this Bayes theorem. So now what you basically did is this thing. The probability of hypothesis given some evidence. This is how Bayes theorem is usually written. You have test and hypothesis. Probability that you have hypothesis given the evidence. Okay. So what you basically try to do is probability of evidence given the hypothesis multiplied by probability of hypothesis divided by probability of evidence. So how did we write this? So we write in this chunk. So this is written in the summation part. So this over here. So these things, this basically is probability of E given H. So this is probability of description given that it was a librarian multiplied by probability of librarian. Okay. So then we made the calculation. So out of this we came out to be with this number. So we said 4. This is the 4, and then we again said this probability of D given L, probability given that the librarian description multiplied by probability of L, and then this is opposite. This is probability of description given he is a farmer into probability of farmer. Librarian given the description. This is what we had to compute. The probability of librarian given. So what I said is, according to the Bayes theorem, so this should be probability of the description given that the librarian was found multiply probability of librarian. Okay, and divided by probability of the description. Okay, now probability of description, if you see the probability of description, it is somehow spanned. The probability of description can be seen like this. So it can probability of description, it can be the librarian. This can be we can break it down. So we can break it down into two cases. We can break it down into probability of description given the librarian multiplied by probability of librarian, and non-lab, that's farmer. That is probability of description given farmer multiplied by probability of farmer. Okay, we can add them to come up with this probability of description. That's why these two terms came over here, the one term and the second term. Okay, this over here is sometimes called as total probability that we again saw. So I made a diagram also like this. So let's suppose you had this event D, you had the event D like this. Okay, now you have these two events. Let's suppose this event is L and this event is F. Okay, now in order to compute the probability of D, so what you can do is you can break it down. You can say this is probability of L intersection of D plus probability of F intersection of D. Probability of this portion, basically this portion, and plus probability of this portion, intersection portion. And then how can you do it? So you know, by the multiplicative rule, you can write probability of L multiplied by probability of L given L D plus probability of F into probability given F of D. I think this is the multiplicative rule that we saw. Any questions on this? Like pretty easy. I just broke this down. This probability of D, usually denominator is broken down into different portions. So probability of this D of happening, because you have multiple cases, so that's why you break it down into like this. Okay, and this is pretty clear. This thing over here. So these 4. How did we come up with this 4? This 4 basically is probability that we have this is a librarian. So what is the probability that this is a librarian? We had some prior. Okay, so this thing over here is called prior. We had the prior belief, how much librarians and the ratio we had earlier. This is called prior. And this thing over here, once we update the belief, this is called a posterior. What happens afterwards? So prior was what our prior belief was, and then posterior, what happened once we update that belief? So how did we update? This is likelihood. This is called likelihood. Likelihood, that's why we said this is fitting the 40% description. This is likely to fit 40% of description. That means we're computing likelihood. So this is posterior, this is likelihood, and this is prior. So prior belief was this, and this is our likelihood. Okay, probability that given this probability is a librarian, give description, which are like 40% of the people are matching this description. Okay, then we compute it like this. We said there are in total there were 10 multiplied by 0.4, so we came up with 4 numbers. So this is the calculation we came up with over here with 4, and then we broke this down into 2 cases, one for the librarians and for the farmers. So here this was 4, again the same calculation that we performed here, and the calculation that we performed for the farmers, that was 20. So we said 4 divided by 4 plus 20, that is 4 by 24. So this is called posterior. What happened once we update the things? So this is posterior, and prior, this is our prior, what we had the prior knowledge of the belief, and this is called likelihood. And in here you have to, again this is for normalization again, and here you have to break it down into cases. So there are different levels in which you can understand Bayes theorem. So one, you can directly come up with this example, maybe just make this square and say, oh, these are different parts. So this is one part and this is the second part. Okay, now before delving deeper and making you understand more of the things, we'll take the question again that we were taking once we were introducing probability. The question goes like this: a laboratory test has 95% of accuracy rate, or which is called as detection rate, that is out of the people, 100 people, if they are diseased, 95% will be accurately mentioned that they have a disease, and that it has a false positive rate. It also has a false positive rate. That means if a person does not have a disease, it will still consider it as positive, but it has very less false positive, that is 1%. So 1% basically means out of 100 people which are not diseased, for 1% it will show it is disease, for 1%. That is for 1% among the 100 it will have disease. So among the whole population, 0.5% of the people have disease. They have the disease actually. Okay, a patient goes to the hospital and gets this test done. Okay, and the test comes out to be positive. Basically, a test says that he is diseased. So you have to compute the probability that a person actually has a disease. Person actually has the disease given that test was positive. So how can you do that?